Ladies and gentlemen, I am honored and proud to have a chance to speak at Iniscom conference today. First of all, let me introduce myself. My name is NgocTuan. I come from Liquidon Technical University, Hanoi, Vietnam. Today, I would like to talk about an efficient side channel attack technique with improved correlation power analysis. My presentations will be divided into 5 parts. The first part is introduction. The second part is background of original correlation power analysis, in short form is CPA. And I will show you some related works that improve the CPA. The next part is our proposed technique to improve the computation time of CPA. The remaining 2 parts are experimental result and conclusion. So let me begin with introductions. As you know, electronic cryptographic devices are widely used today for securing the secret information. However, there are emerging issues about side channel attack. In the scope of statistical power analysis attack on cryptographic systems, 2 efficient techniques were proposed. The first one is well-known different power analysis (DPA), introduced by Paul Kocher and formalized by Thomas Messerschmidt. It uses statistical tools to find out the information correlate to the confidential key. The second one is correlation power analysis (CPA), that's proposed by Breer. It exploits the correlation between the power model and real power consumption in order to leak the secret key. These techniques and measurements are carefully taken into account by embedded system designers to know an attacker can measure the power consumption or electromagnetic emanation, which are 2 of the main physical quantities used for non-invasive attack. In this paper, we focus only on the CPA in order to evaluate the security of the AES cryptography because it is an efficient technique to recover the secret key with a simple power consumption model. And side channel analysis with real devices usually have high levels of noise. Then the efficient attacks requires a large number of power choices. Therefore, finding an efficient way to analyze those power choices is critical. To help you understand our contribution in this paper, I will give you some background about the original CPA. Original CPA used the correlation coefficient to calculate the linear relationship between the real power consumption and power consumption model. Most widely coefficient used is Pearson correlation coefficient, and the formula is shown on the screen as you can see. About the power consumption model, the mostly used model is Hamming distance between 2 relevant values in the same register, or simply the Hamming weight of the particular value. In our paper, we choose the Hamming weight for the power consumption model. This model will calculate how many bit 1 in the results of S-box functions. And the formula of the Hamming weight is shown on the screen as you can see. As mentioned previously, we can see how well the power model and actual power consumption correlations. So from the Pearson correlation formula, we use the formula tree for calculating the correlation of all sample in a power choice with the power consumption model. Because AES is a cryptographic algorithm executing on one byte sparingly, therefore we only focus on a byte that has a lookup position, as illustrated in figure on the screen. To implement Formula 3, we use the algorithm 1 on the MATLAB software. From the original CPA, many works have proposed to improve the efficiency of CPA. So this slide I will show you some related works which focus on the computing effectiveness. In the reference number 7, the authors introduced a selection method that can be used to reduce the number of power choices. It means reducing L. To review the keys, the authors does not show the computation analysis in terms of execution time. And the authors number 8 presented the partitioning power analysis (PPA) technique to combine the technique of DPA, multi-bit DPA and CPA in a single form. Despite the enhancement of CPA, the computation time is not presented in this method. Another technique is presented in the reference number 9. The authors shows a new method to recover secret keys with less power consumption choices than the standard CPA. This technique reduces the number of power choices for CPA, but the author does not give any information of computation time. And most recently, in the reference number 10, the authors proposed an algorithm that is similar to the original CPA. This technique is based on the idea of creating at each point in time a vector of consumption values indexed by the plaintext by values. This method also refers to L and N and has two phases. This method only works well if the number of power choices is large enough. So to tackle the problems in the works mentioned above, we propose new algorithm to implement CPA. As you can see, two figures on screen. The right one is the correlation of all samples calculated by 50 power choices, and it is clear that we have some point have the significantly higher value than the rest, and the red color one is the highest. In this case, we use the algorithm 1 and find out the correct subbyte key is 43. The remarkable thing here is if we calculate with smaller power choice than 50, we still have almost these points have a higher value, as you can see the figure on the left. So our proposed here is divided CPAs in two phases, and the first phase we will calculate to find out the point of interest, which have a higher value than the rest. The novelty of our proposed approach is the optimal chosen parameter. So the figure on the left, we only calculate by a half of power choice, and it's clear that we still have the same positions, have the higher values than the rest. So this is the main technique of our proposal. So in summary, we have two phases. Phase 1, a small number of power choices is used to and denotes as N1. N1 is less than and equal half of N. The equation 3 is applied to calculate alpha highest samples from all guess keys. The values of alpha is much smaller than L. As you can see the figure illustrated on the screen. This is a figure to illustrate taking 10 samples which have highest correlation values. Phase 2, the equation 3 is used again to compute the correlation for all hypothesis keys. However, only alpha samples are calculated instead of using L samples as the first phase. The figures on the right illustrate the correlation of 10 samples calculated in phase 1, and the first point is the highest value. To implement our proposed algorithm, we use the algorithm tool on the MATLAB software. To prove the practical effectiveness of the proposed technique, let me move to the part 4, experimental results. In this experiment, we use the synchronous and low noise power choice of low frequency AES implementation acquired on chip whisper board. And then the Gaussian noise is added to illustrate the real environment. The figures on the screen show the results of proposed CPA technique with the sum of N1 values. The best result of CPA is with N1 equal 1/3 N. And the more noise is added, higher N1 is needed for extracting secret key successfully. To demonstrate the effectiveness of timing execution, the proposed algorithm is implemented with the same configurations of the conventional CPA algorithm. In this experiment, we used a number of power choices in the range from 1000 to 10,000, corresponding to the standard deviation of noise ranging from 0.06 to 0.15, and with N1 equal 1/3 N. These parameters are listed in the table shown on the screen. And the figure on the screen on the right shows the results of experiment. It can be seen that the proposed technique is much faster than conventional CPA. As expected, the values of N1 directly affect the calculation time, and it is effective with the broad range of number of power choice, not only the last number as the reference number 10. So, for conclusions, in this paper, we have proposed a new CPI method in order to recover the secret key. This technique contains two phases. The first phase calculates the number of points of interest of all possible key bytes, very small compared to the number of power choice samples. Then The points of interest are used to compute the highest correlation values of all gas gigabytes. The effectiveness in terms of execution time is demonstrated in experiments with various number of power choices, which have clarified the efficiency of the proposed method. In the future work, mathematical representation and analysis will be investigated in detail. So this is my presentation for our paper. Thank you for your attention.